Sorry? No. So obviously we saw that x was incremented by 1, but because there is a move sx instruction, what will happen is the MSBs will all be filled with 1 1 1 1 1 1 1. Okay. So that turns out that based on the example which we have seen, let me show you this thing 128 with move sx. What will happen is, in our example, it was incremented by 1, so it is FF and then 81. Okay. So Z would be 128, Z would be FF 81, and that is approximately equal to 4 gigabytes. So just imagine what will happen if a 4 gigabyte value is put in over here, a mem copy destination source comma 4 gigabytes. That is actually the total memory that a 32-bit system could address. So if the destination is not that big, the destination buffer is not that big, it will lead to a buffer overflow. Okay, and in the patched version, what will happen is this thing would be just 0000081, that is 129. So what is happening is, in the unpatched version, a mem copy call is made, which is trying to copy 4 gigabytes of value, and in the patched version, we know that it has been reduced to just 129 bytes. Okay, so at this point, we have tried to analyze what the change was and what was the change made by Microsoft in this patch. So how do we exploit this thing? Sorry? Depends. Like, that's true. But what we know, what we want, we are not trying to write an exploit for this, just a proof of concept. So what we know is, somehow if I put this magic number 128 somewhere in this NAPTR record, there is a high chance that I will be able to exploit the vulnerability, right? So I am usually not I'm not an expert with NAPTR record, but this is what a sample NAPTR record looks like. It's really simple to add an NAPTR record to your Windows DNS server. This is what a sample NAPTR record looks like. You just give it a name, a fully qualified domain name, and you see there are these fields over here: order, preferences, flag string, regular expression, replacement domain. So to exploit this vulnerability, you don't have to be an expert with NAPTR records. All you need to know is, I have to put this magic number 128 somewhere in one of these fields so that the vulnerability will be exploited. Okay. So what I do is, I start at putting 128 over here, 128 over here, here, and I try to do an NS lookup, but it would never, the vulnerability was never exploited. Ideally, there should have been a remote buffer overflow, and at least the service should have crashed, but that never happened. So can anyone tell me a better solution? What I could have done to exploit this vulnerability? We know that there is something related to 128 number, and surely there would be a buffer overflow. No, so it turns out it's not that difficult. So what I did is, I saw there are 3 string values: the flag string, service string, and regular expression string. So what I did is, I just, rather than putting the value number 128, what I did is I just put a random 128 characters in there, and then I did an NS lookup, and then the service crashed. It was as simple as that. Any questions? No? So how this vulnerability could be exploited in a real world scenario? So what could happen if, suppose there is what an attacker could do is, he could set up a malicious domain name server with a crafted DNS record, the NAPTR record, and he could just send an email to one of the guys in here. Suppose he wants to target a company name XYZ, what he could do is, he will send an email to a guy in this company saying, hey, could you open this link? This guy would try to resolve that thing, the domain name for this, and it will try to fetch that record. And once it fetches this record, the DNS server over here, if it's a Windows DNS server and it tries to parse this record, at this point the vulnerability would be exploited, and the DNS server running on this system would crash. As simple as that. So the important thing what we want to know over here is, that only the DNS server service that is running on the machine would crash, not the entire operating system, because it's not a kernel level vulnerability, it's just a vulnerability in the application mode, application layer, the DNS server application, not the kernel vulnerability. So let's try to do something more harmful, where we would try to bring down the entire server, and let's try to exploit a vulnerability in Windows kernel. Any questions on MS11 058? No? So this brings us to another example, next example of MS11 077. MS11 077 was released last year in October 2011, and what it did is it fixed 4 vulnerabilities in Windows kernel. Again, if you look at the advisory, vendors don't give out a lot of details. It just says that MS11 077 fixes a remote code an elevation of privilege vulnerability because of insanitized inputs. That is it. They don't give you a lot of details, what parameter was not sanitized or things like that. So for this talk, we'll be concentrating on CVE 2011-1985, and it was an elevation of privilege vulnerability, and this is what the results from turbodiff look like. So it tells you that there are many functions that look suspicious to it. Some were classified as suspicious ++, some were marked as changed. So can anyone tell me, like in the previous example that we saw, only 4 functions were changed. But if you look at this thing in this patch, there are many functions that were changed. Any guesses why the number of changes are so much? Sorry? Yeah, that's correct. So we saw in the previous one, Microsoft only fixed 2 vulnerabilities, but in this patch, Microsoft fixed 4 vulnerabilities. So obviously, because they fixed a lot of things, there are high chances that they need to modify a lot, do lots of code changes, and hence the number of changes are more. So what I did is I started looking at each function one by one, and then I saw that there were 3 functions that all start with anti-user fn. Anti-user fn, 3 functions starting with anti-user fn, and all the code changes that were made to these functions were all the same. So basically, whatever change was made to one function was basically copy pasted in all these functions. Okay. So for our analysis, what I did is I took one of the function named anti-user fn inl box string. Can everyone see this in the red? Okay. So what turbodiff tells us is that for this function there was a code block change. A couple of instructions was added over here, and there was this whole block of code that was added by this new version of the file. So let's try to analyze it. So what we see is you start comparing each instruction one by one, and there was this one additional instruction that was added. Compare ECX, FFFF, FFF, this whole bunch of FFs. And another block of code was added. So let's see what is going on in here. We know that compare ECX, FFF was added. If you see the instruction over here, move ECX EBB plus arg of 0. This is basically the whatever is the first argument passed to this function was moved to ECX. ECX is then compared with this whole bunch of FFs. This is nothing but -1, 2's complement of -1. And if it is not, if it is -1, the whole, it goes into this block and calls a function with set user set record. So let's see what's going on. ECX is compared with if ECX is -1, a function call is made set last error, and function set last error with code 578H and then return. So what is basically going on in here is, in the unpatched version, there was no comparison like compare the first argument with -1 or anything. Whatever argument is passed to that function, it happily accepted that argument and it continued processing. But in the patched version, what is happening is, the patched version is explicitly taking the first argument of the function, it is comparing it with -1. If it is found to be -1, it is not happy, it sets an error and it bails out of the function. Okay. So I did a bit of a research, googling on what is this error is, what is 578H is, and it is a system error code for invalid window handle. So let's try to see what's going on. In the patched version, whatever is the argument, it doesn't care, it just accepts it, processes it, and goes out. But in the patched version, what it is trying to do is, it is taking the first argument, comparing it with -1. If it is found to be -1, it is not happy, it sets an error and it bails out. So how do we exploit this vulnerability? So let me go over again. In the unpatched version, whatever is the first argument, it accepts the argument, processes it, and it is happy, whatever is the argument. In the patched version, what it is trying to do is, it takes the first argument that was passed to this function, compares it with -1. If it is found to be -1, it is not happy, and it sets an error and it bails out. So if you were to exploit this vulnerability, how would you do it? Sorry? Yeah, that's correct. So we know that whatever is so the patched version is looking for this argument, it is not happy when it is -1. So if you were to exploit this vulnerability, just set this argument to be -1 and see what happens. So how do we exploit this? Argument has to be -1, and there was a little hint when I did a Google search about it. It said it sets an error before it bails out. The error which is set is invalid window handle. So this gave me a bit of an idea that first of all I have to set this argument to be -1, and it is explicitly telling you that I am not happy because it is an invalid window handle. So what you do is, we know that this gives you a little hint that the first argument is of type window handle. Okay, so this is a proof of concept for MS 1177, just 2 lines of code. You run it on your Windows machine, and it will be a blue screen of that there. So yeah, any questions? No? Okay. Sorry? Yeah, I have a good blog about this. I think I have a link to that blog. So because what happens is, if you see this function anti-user NL box string, this is a kernel function. You cannot just give it a call directly. So you need to know how to reach that function, how to hit that function. So that's I have a blog about it. Just go to it, and it has pretty much everything what you need to know about this thing. Okay. Any other questions? Okay. So what we have seen until this point, the point which I wanted to highlight is that this technique is really very simple, and what penetration testers could do is they could use this technique to develop their own custom exploits, and they are just not limited to the exploits that are available from exploit packs. They could create their own proof of concept and test it and engage them again, use them in their engagements. So it turns out that this technique is not just only useful for penetration testers, but there are these bunch of guys who are already using this technique. And can anyone guess who are already using this technique? So yeah, malware authors. Malware authors are the ones who are using this technique a lot. It is very helpful for them. So whenever these patches are released, what they would do is they would start doing binary diffing, and they would try to come up with exploits so that they could use it. So a very good example of this is MS-12004. It was released in January 2012, and what it did is it fixed 2 vulnerabilities in Windows when handling the MIDI files. Everyone know what a MIDI file is, right? These are like really small music files. Okay. So for this talk, I'll be concentrating on CVE 2012-003, and it's a remote code execution vulnerability when parsing the MIDI files. So the nature of this vulnerability, which makes it more lucrative for the malware authors, is first of all, it's a remote code execution vulnerability, and secondly, if I send you a link which has a MIDI file, your browser will try to parse it there and there. So basically, if you are not patched, and if I send you a link to an exploit and you click on it, basically you are owned by that time. So Let's do a binary diffing again. You see that TurboDiff tells us to fix this vulnerability, Microsoft did not change, just change one function to fix this vulnerability. All the functions look identical and there was only one function that was changed. So let's try to analyze what the function change was. So the function name is MIDI outplay next poly event. We don't care about the function name. And if you start comparing each instruction one by one, you will see that there was this one additional instruction that was added, AND BL, 7FH. So let's try to analyze what this AND BL, 7FH is. So what is happening over here is, so there is this one variable that was moved to BL, and it is compare, and then logical AND was done against 7FH. So what is happening over here is, whenever there is a, what AND logical AND does is, if the value in BL is less than 7FH, it is kept to that value. But for if the value of BL is more than 7FH, it is reduced to 7FH. So what's happening over here is, in unpatched version there was no sanitization whatsoever. Anything you pass to it, it was happily accepting it. But in the patched version, what is happening is Microsoft is explicitly checking one variable, and it is not happy when if the value of that variable is found to be greater than 7FH, it is reduced to 7FH. So this is the only change that was made by the function. So what was the change? Patch is checking for a variable. It is, if it does not want this value to be greater than 7FH. So how do you exploit this vulnerability? That's right. So we know that there is this one variable which the patch is trying to check, and it is not, and it is setting a limit to it. So if you want to exploit this vulnerability, just pass a value that is greater than this limit, right? So turns out this value which it was trying to check is the note number parameter for a MIDI file. Now I don't have an exploit for it. I do have an exploit, but I cannot show you because it's a MIDI file. So if any guys are interested, just send me an email and I'll be happy to send you a proof of concept exploit for this. So guess what? So this patch was released on 10th of January 2012. Any guesses when was the first malware found in the wild trying to exploit this vulnerability? Sorry? So it turns out for malware authors, it is not just, they don't want to crash your system, they want to get reliable code execution. Obviously, if you are good with diffing things, you could have a proof of concept for this in just one day. But to get reliable code execution, it would take you a lot of time. It will take you some time to develop a sophisticated exploit. Still, they were able to do it. So any guesses? How long would it take them? Okay, so the first exploit that was found in the wild trying to exploit this vulnerability was found on 26th of January 2012. So just imagine, like 16 days after the patch was released, there is already a malware in the wild trying to exploit this vulnerability. On the day, even this is a privately reported vulnerability, so before 10th of January there was no exploit out there. But just as soon as the patches were released, within 16 days, there was a malware out there who is trying to exploit the system, your system. So better patch your system fast. So what we have seen until this point is this technique is useful for penetration testers. Malware authors are already trying to exploit use this technique. But what about security researchers? How can they come up with new vulnerabilities? If you guys are trying to do vulnerability research, how could you come up with new vulnerabilities just based on security patches? So it turns out the hard truth is patches are not always done right. These patches are supposed to fix vulnerabilities, but they often introduce new vulnerabilities in your system. A very good example of this is PHP 5.3.9. It was released in January 2012, and it fixed so PHP 5.3.9, it was released to fix hash collision denial of service vulnerability. Does anyone have any idea what a hash collision denial of service vulnerability is? No. Okay. So hash collision denial of service vulnerability, it was a very popular vulnerability, and like it affected many web servers. So even Microsoft had a patch for this. Microsoft fixed it with MS11 100. Also there was a patch for Tomcat fixed it. Like, so what basically a hash collision denial of service vulnerability is, what you do is you have a web server and you just bombard it with lots and lots of post variables. So when you do a post request, what happens is these variables are stored on the web server in a form of an hash table. So the idea is to send lots and lots of post variables, hoping that these variables will cause hash collisions on the web server and try to bring down the web server. It was a very popular vulnerability and affected all the web servers. So how did PHP 5.3.9 fix this vulnerability is, what happened? Microsoft crashed. Really?